So now that we know what a function from Rn to Rm looks like, let's talk about how we can take the derivative of such an object. And it turns out that the proper way to take the derivative of a function from Rn to Rm is to associate it to a certain kind of matrix. So here's the technical definition. The Jacobian derivative of a function f from Rn to Rm is the m by n matrix denoted by df, where d is capital here. And this is a matrix that is organizing all of the partial derivatives of all of the coordinate functions of the function from Rn to Rm. So if we look at the 1,1 entry of the Jacobian derivative, this is the partial derivative of f1, that's the first coordinate function of f, with respect to x1, the first input variable. If we look at the 1,2 entry, this is the partial derivative of the first coordinate function with respect to the second input variable. And if I keep going down the first row, I end with the partial derivative of the first coordinate function with respect to the nth input variable. In the second row, we're looking at the partial derivatives of the second coordinate function with respect to each of the input variables. And we keep going down until we get to the last row, which is the partial derivatives of the last coordinate function with respect to all of the input variables. So there are two different ways to think about this. I like to think of in terms of columns or in terms of rows. If I think in terms of columns, I can think of the first column of this matrix as organizing all of the partial derivatives of all of the coordinate functions with respect to the first input variable x1. Then if I move to the second column, what I'm looking at is all of the partial derivatives of all of the coordinate functions with respect to the second input variable x2. And if I keep going column to column, what I'm doing is I'm taking partial derivatives with respect to all of the coordinate functions with respect to the next variable. So in the last column, what we're doing is we're organizing all of the partial derivatives of all of the coordinate functions with respect to the last input variable xn. On the other hand, I can think in terms of rows. If I think in terms of rows, what I'm doing in the first row is I'm taking a partial derivatives of the first coordinate function with respect to all of the input variables. If I look at the second row, I'm taking all of the partial derivatives of the second coordinate function with respect to all of the input variables. And if I look at the last row, I'm taking partial derivatives of the last coordinate function, f sub m here, with respect to all of the coordinate variables. So that's two different ways to think about it. But the important thing here is that in the Jacobian derivative, for a function f from Rn to Rm, the Jacobian derivative is an m by n matrix whose ij entry is the partial derivative of the ith coordinate function with respect to the jth input variable. So when we take a derivative of a function from Rn to Rm, what we're doing is we're constructing an m by n matrix. So here's our first example. Here I'm looking at a function f of two variables, x, y, that produces two outputs. So this is a function from R2 to R2. F sub 1 here is x squared times y, and f sub 2 here is xy minus sine of y. So how would I construct the Jacobian derivative? Well, since this function is from R2 to R2, I know that the Jacobian derivative, df, will have 4 entries in it, arranged in a 2 by 2 matrix. The 1,1 entry should be the partial derivative of f1 with respect to x. Well, f1 is x squared times y, so its derivative with respect to x should be 2xy. If I go to the 1,2 position, this should be the partial derivative of f1 with respect to the second input variable y. f1 is x squared times y, so its derivative with respect to y is just x squared. If I go to the 2,1 position, this should be the partial derivative of f2, the second coordinate function, with respect to the first input variable x. And in this case, since f2 is xy minus sine of y, the partial derivative with respect to x is equal to y. Finally, in my 2,2 position, I should be taking the partial derivative of f2 with respect to the second input variable. f2 is xy minus sine y, so the partial derivative with respect to y should be x minus cosine of y. So when all is said and done, we've constructed a 2 by 2 matrix when we construct the Jacobian derivative of this function from R2 to R2. So indeed, df here is 2 by 2 because f goes from R2 to R2. Let's look at another example. Here I have a function g of two variables, u and v, and g produces three outputs. g1 is equal to u, g2 is equal to u times cosine v, and g3 is equal to u times sine of v. So what will the Jacobian derivative look like? Well, this is a function from R2 to R3, so the Jacobian derivative should be a 3 by 2 matrix. The 1, 1 entry should be the partial derivative of g1, which is just u with respect to u, so that's equal to 1. In the 1, 2 entry, I'm looking at the partial derivative of g1, which is u, now with respect to v, though, which is equal to 0. In the 2, 1 entry, I'm looking at the partial derivative of g2, u times cosine v, with respect to u, well, that's equal to cosine v. And then in the 2, 2 position, I'm looking at the partial derivative of g2, which is u times cosine v, with respect to v now, which should be negative u times sine v. In my 3, 1 position, I should be taking the partial derivative of g3 with respect to u. Well, g3 is u times sine v, so the derivative with respect to u is sine v. And in the 3, 2 position, I should be taking the partial derivative of g3 with respect to v. Again, g3 is u times sine v, so the partial derivative with respect to v should be u times cosine v. So in this situation, the Jacobian derivative ended up being a 3 by 2 matrix because this is a function that goes from R2 to R3. Let's do another example. So here I have an even more complicated function, bold h here. H accepts three inputs, x1, x2, x3, and uses those three inputs to build 1, 2, 3, 4 outputs. So this is a function from R3 to R4, which means that the Jacobian derivative should be a 4 by 3 matrix. So rather than look at this entry by entry, I'm going to think in terms of columns here. So how could I build the first column of this Jacobian derivative? So this should say dh, by the way. Well, in my first column, what I'm doing is I'm taking the partial derivatives of all of the outputs with respect to the first variable x1. So the partial derivative of x1 is just 1. Partial derivative of 3x1 squared times x3 should be what? 6x1 x3. Partial derivative of 4x2 squared minus 22x3 with respect to x1 is 0. And the partial derivative of x3 times sine of x1 should be x3 times cosine of x1. So I take all of those partials with respect to the first input variable x1 and place them in the first column of my Jacobian derivative here. In the next column, I'm going coordinate by coordinate and taking partial derivatives with respect to x2 now. So I should end up with zeros in the first two positions because there aren't any x2s here. In the third position, I have this term that has 4x2 squared, which becomes 8x2. And then there is no x2 in the third position, so I get another 0 there. For my third column, I'm now taking partial derivatives of all of the coordinates with respect to the third input variable. So in my first position, I should have a 0. In the second position, since this is just an x3, I get 3x1 squared. In the third position, in the third row, I should end up with negative 22. And then in the last position in the third row, I should end up with sine of x1. So here I went column by column instead of entry by entry. But the point is that this Jacobian derivative is a 4 by 3 matrix because this function goes from R3 to R4.